So, we go into now a topic in blast furnace iron making, that is raw materials and burden preparation. This is a very important topic indeed. And this is, as you all know, it is lecture 3 of this course and 1 out of 5. That is, I said I will take about 5 lectures on blast furnace iron making. Yesterday I took the first lecture, today is the second lecture. So, this is 2 out of 5 on blast furnace iron making. So, before we start the discussion, I think let me draw the line drawing so that we can refer to a blast furnace very frequently in this course during the lecture, and this is so that is how the lining material. So, that is what it is, and then possibly I can draw something like this, and then I can draw to show the different lining materials are there, and this is what it is. And if you, I will keep on building it on the other side as we go on to the course. So, we have the slag notch as I have indicated, and the metal notch yesterday, and this is our so roughly this so I will connect it like this, and then we can go like this, and then we can go possibly like this. Yesterday I had indicated that from the top, and I have also said that you got to refer to an internet site in order to see the construction of the top part, which happens to be too complicated to be drawn on the board, and that I am not projecting slides. So, I think by now you must have glanced through internet and found out that how complex that structure at the top is. So, through the top, okay, the arrangement is not of importance to us as far as the science of iron making is concerned. So, we introduced yesterday, I have told you, lump iron ore. So, IO is iron ore and this is L, lump iron ore. We also put in limestone, we also put in coke, and as I said that we have sinters and pellets, which are man-made iron bearing material. These are the feed material from through the top. Then we have feed material, this is preheated air, that is all. And as we will study later on, the blast furnace, we have also many injection facilities in a modern blast furnaces. For example, through the stack we may have what is known as a stack gas injection. So, that is also a feed. Clean blast furnace gases sometimes are fed into this, sometimes natural gases are fed into this through the tuyeres along with air. Sometimes, as we will see in modern developments, that we want to use pulverized coal. This means basically coal dust, that is what we inject through the tuyere. So, a part of the carbon load which comes into the furnace through the top is replaced by injecting sometimes lime dusts are also injected. So, all this constitute heat feed to the blast furnace, and as you will see that there are material feed, and because we are talking about preheated air, and therefore, there is a sensible heat input also. So, there is a feed to the furnace comprises of both heat and mass, and this provides you a list of it. Now, if we refer to whatever is charged from the top, this component is referred to as the burden material. So, I would say the blast furnace burden material comprises of iron ore, limestone and coke predominantly. There may be variations of the iron bearing material. So, lump iron ore, sinters and pellets, they comprise what is known as collectively as the iron bearing burden material of the blast furnace. Okay? And then some blast furnaces also charge dolomite into the blast furnace, which is also calcium oxide, calcium carbonate, magnesium carbonate combined. Limestone is calcium carbonate. Okay? We do not charge lime into the blast furnace. We will see when we study steel making, we will be charging lime and not limestone into a steel making reactor. Lime is a very important constituent, and it will be clear as we go on with our discussion on the subject. Now, as far as this material is concerned, we have to study that how the burden materials are prepared. As such, we cannot get the ore and dump it into there. There are certain restrictions into the blast furnace that what can you put in. For example, I can get limestone from mines, but that limestone it contains, for example, calcium oxide, carbon dioxide, there is calcium carbonate, and it contains MgO, it contains other impurities as well. What is the purity of limestone that is required in order to be fed into a blast furnace? What should be the physical characteristics of it? What should be the size range of it? What should be the shape of it? So, as mined feed materials cannot be charged into the blast furnace as it is, so it will require some kind of a preparation, and that is why the one part of the discussion is burden preparation, that how do you get these materials from mines and then make it suitable for charging into a modern day blast furnace. And we will see that the physical and the chemical characteristics of the burden material. The physical characteristics, we all know what does that mean. Physical characteristics means I am referring to the size of the particle, the shape of the particle, the strength of the particle, and so on. Physical characteristics as well as chemical characteristics. When you talk of chemical characteristics, I would say, the question would be, what is the fixed, what is the extent of iron content or the grade of iron? The iron content in an iron ore is termed or evaluated in terms of grade. Okay, that is the percentage of iron in the iron ore. So that is also, there is a chemical parameter. So chemical characteristics, the reactivity of coke, for example, is an important parameter, and so on. So physical characteristics and chemical characteristics of the feed material or the burden material exert profound influence on the performance of an iron blast furnace, and we will see that as the discussion goes on. So physical characteristics, as I said, says shape, size, as well as strength. Chemical characteristics, I will say composition, okay, reactivity, and other chemical characteristics, how much impurity is there, and so on and so forth. You can imagine that if you have, iron ores are available in various grades. You can get 65% iron containing iron ore, you can get 35% iron containing iron ore. But if you charge a 35% in iron in blast furnace, the furnace will be producing more slag than hot metal. Actually, a modern day blast furnace may not be viable for charging any iron ore that contains about 40-45%. So in that case, what do? We all know beneficiation is an important tool. That means we will do extraneous concentration arrangements, that is the subject of mineral engineering, whereby the content of iron in the iron ore is going to be enhanced using some mineral beneficiation techniques. That is again a different subject, but I just thought that I will mention it in this particular context. These burden materials, for example, has evolved and is continuously evolving for, because the market scenario is changing, the environment is changing. So therefore, the burden material characteristics is changing or has changed over the years. For example, I would say when we were students, 30, 40, 45 years back, in those days, the coke rate of the furnace, that how much coke is going to be consumed. I will explain what is the term, when you talk of the burden preparation, then I will discuss about how you can get coke. Coke is not a naturally occurring material, so it is to be prepared. So when we were students, then typically the coke rate of a furnace, the coke rate is expressed in terms of kg of coke per tons of hot metal, which is in short in this course we will write small t, small h, small m, which essentially means that it is, some people write it capital T, capital H, capital M also, tons of hot metal, that is what it is. And hot metal is what? Which flows out of the furnace, product of the blast furnace. So, these are product, these are feed material, and I would say the product of the blast furnace is the off gas and slag as well as metal. These are the, so you can have input output balancing also done, the material balance calculation, which I will be talking to you in a later bit. So, when we are students coming back, this is a common figure globally, about 800 kg of carbon per tons of hot metal. Okay? And today there are many furnaces which operates at 500 kg of coke per ton of hot metal. And our target is, we want to get into the theoretical maximum, that is 350. A blast furnace, we will see, cannot be operated with zero coke. The threshold amount of coke which is necessary, because coke has an important function which we will outline later on, you will see 300 kg per tons of hot metal is the bare minimum coke rate that is possible in order to run. Energetically, by calculation, performing calculation, you can show that you can replace the entire amount of coke from auxiliary source. If you supply heat, if you supply a reductant like hydrogen, it is possible to theoretically make iron, extract iron, but on the other hand, in a blast furnace it will not be possible, because coke has an important function in the blast furnace, as we will discuss as we move along with today's discussion. So, this is our target. Now, when we were students, those days sinters and pellets have barely come to be introduced from the top, okay? And today there are furnaces which are operated with 100% sinters and 100% pellets, okay? So, similarly, there are various furnaces in which limestone is rarely charged as pure limestone, but the entire limestone load is put into the furnace via the sinters and the pellets. So, tremendous amount of evolution has taken place, as far as the engineering of the burden material is concerned, and which has evolved over the years, and we are still not satisfied. For example, we want to reduce carbon to the lowest possible value, because the blast furnace is known to be producing an enormous amount of carbon dioxide, which we know is an important component of GHG, which is greenhouse gases, and which leads to the global warming. So, we have to improve the carbon credit of iron making processes, and iron making is this usage of fossil fuel in iron making, which is coke, which comes from coal, is the largest contributor as far as the iron and steel making industry is concerned in terms of its carbon dioxide production, and that needs to be minimized. So, there is a continuous thrust to make when you talk of green iron making, green steel making, that is the direction in which we really want to move, that from higher coke rate to a lower coke rate. There are various other points in iron and steel making circuitry. For example, where you make sinters, there also carbon requirement is pretty high, and that tends to generate a lot of carbon dioxide. So, unless and until we do optimize recycling, use the off gas or the wastage materials efficiently, we will not be able to have a good carbon footprint for our process. And today's struggle in the steel industry, which we will all be working towards in the next 20-30 years, is how to improve the carbon footprint of the process and how to make it environmentally more friendly. And one such direction is a continuous struggle in order to reduce the coke rate of the blast furnace, which now in a very good blast furnace is about 500 kg per tons, and our target in future is that we will get to about 350. Not only lump iron ore has been replaced by sinters and pellets, even in blast furnace feed materials, automobile tires have been charged into the furnace, DRIs have been charged into the furnace, all sorts of permutation and combination are being charged, and with one single objective, that we want to improve the process performance in terms of its productivity, in terms of its environmental impact, and all these kinds of things. Okay? And yesterday also I told you the DRI, which basically is direct reduced iron. Direct reduced iron means it is not Fe2O3 you take, and if you remove a part of oxygen, not the entire oxygen, so what happens? This becomes a mixture of Fe2O3, Fe3O4 or FeO, okay, because you have partially reduced it, and that partially reduced mass is basically referred to as DRI or sponge iron, which we will see in this course is an important feed material for electric furnace steel making. But today in many furnaces around the globe, DRIs are also increasingly being fed into the blast furnace in order to improve its performance. So, this preliminary discussion or the introductory discussion really tells us that, well, the Bardon material is very, very important for us, okay? And the Bardon material has been evolving, and we must understand that, several points in order to appreciate that, what is the impact of the Bardon material on the furnace performances. Now, as far as the iron bearing material is concerned, the iron bearing material, it is the basic constituents which supplies iron, okay? There is a gas solid reduction reaction between the carbon monoxide and carbon dioxide, carbon monoxide and iron ore, as I have indicated. So, there is kinetics of reduction which comes into the picture, which determines the rate of iron production. The rate at which you will be able to reduce iron ore, okay, will be reflected in terms of your productivity. Now, on top of that reduction within the furnace, we must understand that, as I have indicated, that we have 1900 degrees centigrade near the raceway region, the temperature, and that at 1900 degrees centigrade everything becomes liquid in the furnace. It becomes essential that, suppose if this area is completely liquid, then the gas will not be able to penetrate it. So, we require some kind of a permeability in this high temperature region, and that permeability is ensured by coke. And coke, what happens? Coke is, for example, iron will get reduced at high temperature here, then the iron will get liquefied here, and then it is iron. Then we have calcium oxide, silicon dioxide, etc., all combining, they form liquid slag. So, everything is liquid, but not the coke that we have charged. Coke only oxidizes. Coke only undergoes gasification reaction, okay? And gasification reaction I am going to explain in a bit. So, coke undergoes only reaction or combustion with oxygen, but it does not melt here. So, coke, and that the gas is not able to penetrate to the bottom. So, all the coke never gets burned. There is a surplus amount of coke, and that surplus amount of coke is needed in the blast furnace operation in order to provide the bed permeability. Otherwise, the gas will not be able to flow. Okay? The furnace is going to be flooded with liquid, both metal as well, carbon rich metal as well as slag. So, therefore, as I said, that this comes into the picture that coke is an important material, and coke gives us sustains the bed, and it helps maintain the permeability in the system. Now, other than that also, all this material we must understand are under tremendous amount of pressure. The Bardon load, the furnace is 35 meters. So, you can imagine that as the particles are descending, the temperature is increasing. So, therefore, thermal shock is there. There is the expansion of materials, there are thermal stresses into the materials, and as well as there is a physical load. There is an abrasion between the particles as they descend down. So, the particles have to have really good strength. If the particles do not have good strength, in that case what happens is the particles are going to be easily eroded away or broken into small pieces and then taken by the off gas itself, defeating the whole purpose of iron making. So, the strength of the Bardon material is important. The reducibility of the ore is important, that we have iron ore, as I have indicated, and the carbon monoxide. I do not want carbon monoxide to only react at the surface of the ore particle. I want the carbon monoxide to go everywhere inside and reduce whatever iron is present. So, therefore, the physical characteristics of the ore is very, very important. Gasification reaction is, this is gasification reaction, CO2 gas plus carbon solid is equal to 2CO. This is a highly endothermic reaction, and this is one of the major cause. This reaction takes place because now what happens is there is carbon dioxide is in the upper part of the furnace. So, you have carbon monoxide which is generated, then the reduction takes place, and then what happens is that after reduction, carbon dioxide which is generated because of presence of excess coke, some amount of reformation of carbon monoxide takes place. So, you have carbon monoxide which is generated here, okay, and this carbon monoxide becomes carbon dioxide as the carbon monoxide will reduce iron ore, and then somewhere here, okay, this carbon dioxide can react because we are charging coke. If the thermodynamic conditions are favorable, in that case these reactions can take place. That this reaction is termed as the gasification reaction, and gasification reaction also is called a Woodward reaction, or very popular reaction. I will tell you why it is so important, or also known as gasification. I have introduced the term gasification reaction. Gasification reaction has different meaning, but the moment I say gasification reaction in an iron blast furnace, that is the reaction you have to write. So, Woodward reaction, or also called solution reaction. This reaction is an endothermic reaction in the blast furnace. Okay? So, the net heat effect is that it requires heat, and that is why this reaction tends to take place in the upper part of the furnace where temperature is small. Also, we can see that there is a 1 mole of carbon dioxide in the reactant and 2 moles of carbon monoxide in the, so there is a net expansion of volume. So, this reaction tends to take place or is favored when the pressure is going to be relaxed. If the pressure is high, pressure is going to be applied in the blast furnace, in that case what happens, this reaction will tend to go in the reverse direction. So, by controlling the temperature and pressure within the blast furnace, okay, this extent of solution loss reaction or Woodward reaction can be controlled, and this has tremendous influence as far as the thermal economics of blast furnace is concerned, because this is an endothermic reaction, okay, and therefore, this will tend to increase the coke rate that I have indicated, because coke has to do many duties. It has to carry out the reduction reaction, it has to supply heat for melting of various phases. So, and on top of that, if solution loss reaction also takes place, in that case your coke consumption is going to be increased, because the thermal demand of the blast furnace is going to be higher with more amount of solution loss taking place in the reaction itself. Now, given this background, we can now go and start discussing the preparation of the burden material. So, we will understand that why physical and chemical characteristics of the furnaces materials are very, very important. Coke reactivity is a very important parameter that will determine coke consumption. So, the strength of the materials are also very important in this context. The reducibility is very important, the porosities are very important, and all these are not naturally occurring. We have to engineer them, or you have to impart these properties into the raw material. So, therefore, we require quite a bit of burden preparation. I of course cannot do full justice to this particular topic. So, I will very sketchily tell you about the preparation, that whatever we get from mines and how do you go on to prepare the feed material or the burden material suitable for a modern blast furnace operation. Now, let us take the first item, that is the coke. Blast furnace is never fed with coal, but is fed with coke. And why not? Because coal, it has lesser amount of fixed carbon. Coke is much more richer. Coal is has a much lower carbon content. So, therefore, you are charging for an equivalent amount. So, if you charge 1 kg, 1 ton of coal versus 1 ton of coke, in 1 ton of coal you will be charging more impurity material than carbon, which is actually needed for you. Okay? So, therefore, blast furnaces are not operated with, this is one of the adverse reasons. There are many adverse. Coal does not have strength also. If you charge a coal at the top, and this coal is going to crumble into pieces by the time it descends here, it will not be able to withstand the thermal shock in the furnace, it will not be able to withstand the abrasive load, it will not be able to withstand the physical load which will be sitting, and it will crumble into pieces, defeating the whole purpose itself. Okay? So, therefore, coal is rarely used directly into the blast furnace, and it also contains a lot of dangerous volatile materials. For example, you have a lot of alkali material in coal, and if this you are using air, hot air, you have nitrogen, and if you are using alkali materials, if you are using coal that contains alkali material, you can have cyanide formation, sodium cyanide, potassium cyanide, etc. Because the coal is known to contain the alkali elements, and that is going to be particularly, and alkali elements are bad for these refractories actually. They attack the refractories, eat up the refractories, they are very corrosive in nature. So, therefore, there are good number of reasons I can go on and on, which tells us that blast coal is lump coal you cannot charge, big size coal you will not be able to charge into the furnace, that will not be there. But on the other hand, 150 kg per ton of hot metal or 100 kg or 75 kg per ton of hot metal coal powder, good quality, relatively good quality coal powder can be injected into the furnace just to give some relief to the coke rate of the blast furnace itself, because we must know that coal is much cheaper than coke. An increase in the price of between coal and coke, I think I do not have it in my head right now, it is almost by a factor of 10 or more it gets increased. Of all the feed material, this is for sure true, that of all the feed material that we charge into the blast furnace, the cost of coke is the most and it is the major cost component in the operation of the blast furnace itself. So that's why if you go to all private steel industries just outside the purview, the course, and to make it more humorous, I would say that the purchase of coke in all private steel plants are done by people who are very trustworthy to the promoters. Okay? Because you can imagine if you have 22 million tons of steel producing and 500 kg per ton, how much of coke you are going to be coal you have to procure, you can imagine, and that will be a huge amount of cash flow from the company. So you require a very trusted person who will not do hanky panky with the purchasing of this material. So coal cannot be used directly into the furnace, and this coal can be converted into coke, and all coal cannot be converted into coke. There are only certain variety, and that is called a range of bituminous grade bituminous coal. And this bituminous grade of coal, there are several tests it has to be successful, or it has to match with the results of those tests in order to be considered fit for conversion into coke. So it is not just any bituminous coal you pick up. So there is a narrow range of bituminous coal in terms of its composition, in terms of its characteristics, which are suitable for making of coke. And when you take that grade of bituminous coal, which has passed all your tests, so there are tests like, I would say, there are chemical tests, I will write down, but these are there in my textbooks, in extensive detail, and you do not have to really note them down. So, and as I said that perhaps those of you who would like to pursue career in iron and steel making at this stage may consider procuring one of the two textbooks, and in either of the textbooks these characteristics are lined. But anyway, the characteristics that the bituminous coal has to fulfill will fall on several grounds. That is, one is the chemical characteristics. Chemical characteristics essentially will tell us that what are the kinds of impurities, what is the carbon content of the coal. Then you have rheological characteristics, that means when the coal becomes heated up, the coal, how does it flow? Okay? Then we can have petrographical characteristics of the characteristics, which will tell us that what is the origin of the coal and what is there in terms of its microstructural constituents, etc. And there is a mechanical part of it is also that what is the strength of the coal and so on and so forth. So there are series of tests which the coal has to pass, and then once you have picked up the coal which has satisfied all your requirements to make the coke, then the coke also has to pass a number of tests for making it fit to be introduced into the blast furnace itself. We are going to talk about those parameters in a bit time. So if you take that suitable range of bituminous coal and subject it to destructive distillation, that means you heat it to about 1200 degrees centigrade. In the absence of air, then what happens is you get, and how long you heat? You can heat about 24 to about 36 hours. Carbonization takes place, and so in the process what happens is densification of coal takes place, coal becomes cellular structure, the carbon content of the coke increases, the volatile components and other unwarranted materials are driven off. So there is a huge change in the characteristics of the coal, bituminous coal, when you subject that coal for destructive distillation, that means heating in the absence of air, no air. So it is a reducing condition heating for a prolonged period of time, and then the coal gets converted into coke. So, I would say coke is a material which is far more superior in terms of its fixed carbon content, in terms of its impurity content, in terms of its strength, in terms of its structure and appearances. One characteristics which I have not mentioned is the dilatometric characteristics of the coal, which is also that coal, how much it undergoes expansion and contraction during heating itself. These are all very important parameters which one need to consider before buying a grade of coal and subjecting it to the making of coke itself. Now, what are the functions of coke? We will come back to the coke making in relatively more detail later on. So, functions of coke are threefold in the furnace. One is, of course, there are we charge solid materials, we get liquid product here. We have series of endothermic reactions. One such endothermic reactions could be calcium carbonate limestone, decomposition of limestone into calcium oxide plus carbon dioxide gas at around 900 degrees centigrade. There are a host of number of endothermic processes which takes place. So, there is a thermal demand of the blast furnace, that if you cannot supply that much of heat, the furnace will not operate, you will not produce a single mole of iron in the blast furnace itself. So, to satisfy or to fulfill that average overall thermal demand, we require a fuel, and the coke serves as a fuel to the blast furnace. Of course, we are putting in additional amount of heat in the form of blast temperature, which may be 1200 degrees. So, the sensible heat of the blast, we will see how much blast volume is there. This volumes of blast could be 1000 to 1200 normal meter cube per ton of steel produced. And you can imagine, if you have 1200 degrees centigrade as a blast temperature, then how much of sensible heat you are putting in. You are putting in maybe some amount of LPG gases or some amount of natural gases into the furnace, which also have calorific value, but by and large the majority of the major portion of the thermal demand is fulfilled by coke itself in the blast furnace. 10 to 15% may be replaced by the sensible heat. We will do these calculations when we finish discussion about the blast furnace for the next 5 lectures, and beyond the 5 lectures we will talk about that how to calculate the overall thermal demand in the blast furnace and so on. Number 2, that coke serves as a reductant. The coke combusts, produce heat, and that combustion product serves as the reductant. So, it is the gas solid carbon monoxide reacting with iron ore, producing this, you can balance, there is no issue at all. So, these reactions, as you see, that the coke which you have charged, which has produced fuel, also produces the reducing gases, which reduces the iron ore. So, it is the reductant. It does not mean that carbon monoxide is the only reductant. In a modern blast furnace, we will see that we use controlled amount of moisture as an input material into the furnace, because this will give rise to hydrogen, and hydrogen is a better reducer than carbon. Hydrogen molecules are much smaller than the carbon monoxide molecules. So, therefore, the diffusion or movement of hydrogen molecule can be much more easier within the porous ore or whatever ores, because as the ore descends down, the porosity of the solid material, you charge the solid lump material here, okay, and this iron ore material, as it goes down, its porosity is going to be, microporosity is going to be increased because of the escape of oxygen from its matrix. Okay. So, therefore, through those pores it will be easier for hydrogen to diffuse than carbon monoxide, and therefore, controlled amount of hydrogen is also used into a modern day blast furnace, which works as a reductant in addition to the reducing effect of carbon monoxide, which is the result of oxidation of. And most importantly, as I said, that it maintains the permeability of the blast furnace bed. Particularly in the lower part. In the upper part, when the temperature is 900 degrees, 1000 degree, nothing is liquid. There solid lumps are there. So, we have interparticular space through which the gas can flow. But the real problem starts in the lower part of the furnace, where everything is in liquid, and there we need to have, for the gas to flow more or less uniformly across the cross section, we need to have the permeability maintained. And in the lower part of the furnace, where everything in the charged material is liquid except coke, it is coke that helps to maintain the. So, we will have solid particles, and the solid particles of coke, and that will allow us, through which the liquid can go down and the gas can also go up. We will see this interesting aspects of that. If you have, you can imagine that if you have, we will study coke particles like this here, as I have yesterday indicated. So, the liquid will be trickling down and the gas will also be flowing up. If the gas is injected in too fast speed, in that case what happened? It may not allow the liquid to come down. So, there is an engineering aspect of the whole thing. We will discuss this when we talk of the blast furnace operating problems like hanging, flooding, and so on and so forth. So, therefore, in this part, particularly in the liquid part, it is the coke that only provides the permeability to the bed, allowing gases to flow out, flow continuously and exit through the furnace itself. So, these are the three major functions of coke in the blast furnace itself. Now, coke making I have already mentioned briefly. Now, in every steel plant where you make coke, most of the steel plants, as I have indicated, that there are integrated steel plants and there are special steel plants, many integrated small, and I have also said that there are giant blast furnaces, bigger blast furnaces, as well as mini blast furnaces. So, there are many steel plants which have mini blast furnaces, but in our country itself I am talking about, and those steel plants may not have coke production. They will buy coke from a vendor from outside. But big integrated steel mills like Tata Steel, JSW, etc., they all have an in-house coke making plants. So, they buy the coal from the mines, or they have their captive coal mines, okay, or buy from Coal India Limited. You must have seen that if the moment you approach on train to a steel city like Bokaro Steel City, Tatanagar or Bellary, you will see how much of these wagons are carrying exposed coal to the companies, and these companies convert those bituminous grade of coal directly into coke into coke in their own premises. Now, coke making from coal to coke is done in ovens, which called coke ovens. And coke ovens are like huge long batteries, and this looks something like coke oven batteries. If I can draw, you can imagine that suppose the batteries are in this particular direction, okay. So, the length of the battery, so this is the height of the battery and this is the width of the battery. So, it is perpendicular to the board, the width, and this is the length of the battery, and then you will see what you see in the battery is this basically. This is the arrangement that you see. This is the arrangement that you see. So, in this side also it is very long, huge, very long structure, and these are the coal particles. That is the coke oven batteries it looks like. These are coal particles and they are closed from both top and end. and as we said that we require to heat this up. So, this is the heating chamber, this is the heating chamber. How we can heat? You remember yesterday I have shown that we have blast furnace gas which contains carbon monoxide, and after the gas is made to pass through the gas cleaning plant, we have clean gas that contains good amount of carbon monoxide, and that carbon monoxide, so a part of the blast furnace gas can be used to heat up the coke ovens. A part of the blast furnace gas, yesterday I have shown, can be used to heat the blast itself in the stoves. So, during destructive distillation or heating the coal particles in the coke oven for a long period of time, what happens? The coke undergoes many changes physically, but most importantly what happens is that it gives rise to all the volatile components are expelled out of the, okay. So, in the process many byproducts are generated. In earlier, when we were studying chemistry, so many days, so we used to say that every steel plants have a sulfuric acid plant, and sulfur dioxide etc., they really come out once you do the destructive distillation. So, sulfur is eliminated. So, many chemicals are antimony, arsenic, sulfur etc., are driven out during the destructive distillation, because when you heat it to 1100 and 1300 degrees centigrade, it is a reducing atmosphere that they tend to be driven off. And also many organic material liquids are produced like naphtha as well as tar etc. So, huge byproducts are generated during the destructive distillation process itself. These byproducts can be converted, as I have indicated, one of the byproducts could be sulfuric acid, or the byproduct, volatile gaseous byproduct can be burnt in situ here itself, oxidized, and then to liberate the heat. Okay? So, as a result of which antimony can be oxidized, for example, other ingredients present, all these organic volatile materials can be combusted here to release heat etc. So, in one case we can have all the byproducts which are generated are really trapped, and they are used to manufacture other ordinary products, other engineering or commercial products like sulfuric acid, or on the other hand the byproducts are not recovered, but the heat content, the values in the byproducts are used in the form of heat itself. So, we can say one is a recovery type coke oven. Recovery means naphtha is recovered, tar is recovered, other sulfur is recovered, and so on and so forth. The other is non-recovery type, where all the volatile materials will not be recovered, but they will be combusted here in order to generate the heat. That is the essential difference. So, once you put all the lumps of coal inside the furnace, heat it to about 1100 and 1200 degrees centigrade. Okay, this temperature can vary a little bit depending on the characteristics of the coal, and you do this heating about 12 to 24 to 36 hours. Then at the end of that 36 hours, what happens is you get a completely welded mass of coal with each other, because of the many chemical changes, they tend to get welded. So, it becomes a huge compacted mass of coke which is generated, and it is red hot actually. So, after 24 or 36 hours, when we know that optimum carbonization has taken place, all the materials have been, unwanted materials have been driven out, we have got a good structure, okay, and good strength. So, these are the parameters, these are what is the optimum coke making condition is evolved by performing real life simulation, real life experiments on laboratory scale first, and then it is scaled up, and that is how these coke oven batteries are constructed and operated. And this, although I have shown only 3 batteries, there could be 50 such batteries lined up one after another, and I would say one coke oven battery length could be, you can imagine, more than the span of any of the hall 1 or hall 4 or something like that. It is even longer than that. So, there is going to be huge, because the requirement is 500 kg per ton. If you have a if you are in one premise, if you are producing 22 million tons. You can imagine how much of coke is going to be necessary. So, it is not just one battery or two battery, it is going to be hundreds of batteries lined up. So, I only have given you a section, and that too the line drawing of the section, not the details of it. So, after about 24 and 36 hours, when the requisite quality of coke has been imparted in coal, this is now ready to be taken out, and now it becomes a big problem for us, because the moment it comes in contact with air, lot of carbon is going to be immediately oxidized into carbon monoxide or carbon dioxide. Okay? So, spontaneous reaction with atmospheric oxygen will take place the moment the doors are lifted and we try to bring in contact. So, there is an important step called coke quenching, and that coke quenching basically is done with, can be done with water, but this is a very dangerous step actually. So, if you put the red hot, how it is done, there are actually on a car there are rams, and those rams would move like this. So, the ram has a plunger type, as a plunger which has the same sectional size as the opening of this particular battery. So, the car will come, push the plunger inside, and from the other end the mass of coke will fall down, and the moment it falls down on the ground, it breaks into pieces, okay, because it has been loosely welded with its surrounding particles. And on that, when you put in water, in that case what happens, huge steam plume is generated. But of more concern is that because the coke in the process of escape of volatile materials etc. have attained a cellular structure, lot of water tends to go inside coke, and what you are now doing is that through coke, if it contains significant amount of the quenched the water that you have used for quenching, so you are charging in water into the blast furnace itself, and water is very dangerous in terms of the thermal loading of the blast furnace, because of the fact that we can have carbon, and this reaction you have studied in grade 10, which is the popular water gas reaction, and this becomes rampant in the blast furnace. It is beneficial provided water is controlled, because as I said, hydrogen is a superior, if you have too little hydrogen, no good. If you have too much hydrogen, no good, but if you have an optimum amount of hydrogen in the gaseous mixture, that could be beneficial, because hydrogen is a better reducer because of its ease of diffusing into the iron ore and reducing it. So, therefore, and this reaction is an endothermic reaction. So, widespread contamination of H2O, contamination of coke by H2O during the quenching stage, and subsequent introduction of those wet coke into the blast furnace can be detrimental as far as the thermal loading of the blast furnace is concerned, because of this water gas reaction, which will be rampant in the blast furnace and which is endothermic in nature, causing an increase in the thermal load of the furnace or thermal demand of the furnace itself. So, alternative is people tend to do partly water quenching, and also they do liquid nitrogen. This is very expensive actually. So, if an industry is buying coke from an external source, one of the parameters, it will not ask only that how much of fixed carbon is there, it will say that what is the residual moisture content in your coke. That is very important. That will determine, you may give me 99.5% coke, but if it contains too much of a water, that water is going to eat away all my coke, and it is the fixed carbon has no relevance in such context at all. So, therefore, the efforts must be made such that the coke does not get laden with moisture beyond a certain, there is an acceptable limit of moisture content of the coke which can be used and charged into the blast furnace. So, we have studied the function of coke, we have briefly looked at the recovery and non-recovery type ovens. I hope this is clear to you. So, coke making is over, and now we will see that what are the requirements of coke. Well, because this coke we have made, now it has to fulfill certain requirements, so that we can consider it to be fit for charging into the blast furnace. Okay? And we have many physical and chemical requirements, chemical and physical requirements. Chemical requirements, as I have requirements that coke has to fulfill. So, we have function of coke we have done. I have given an introduction of Barden material, then function of coke, coke making. The third topic here is very briefly is requirements of coke. Now, most of the time what happens is that we have, we can study the properties of coke outside the blast furnace itself, but that may not reflect. Suppose I can take coal in my laboratory and determine the strength of coke, but that may not be, that cannot be translated to the real life scenario, because within the blast furnace the coke is subjected to different kinds of environment, chemical and physical environment, as it descends down. So, therefore, in an isolated way, if we study the properties, that may not be very useful in terms of course, fixed carbon is fine, fixed carbon I can determine in laboratory, but the strength of the coke at room temperature may not be relevant to the actual strength of the coke that it exhibits during its descent through the furnace itself. That we have to remember. So, chemical characteristics, as I have indicated, fixed carbon is one important parameter, that is, that we will say. The reactivity of the coke is also a very, very important parameter. Okay? Now, we must understand that the coke strength in the furnace is also, the coke undergoes fragmentation in the furnace because of various factors. One such factor is, of course, the load which is sitting on it. The second is about the abrasion which takes place between the particles, relative motion of the particles or the coke particle and the wall of the furnace, and the third is because of the gasification reaction. And the coke also undergoes, as I said, that the dialectrometric property is important, because with heating, if the coke undergoes too much of an expansion or contraction, in that case what happens, that the coke may develop internal stresses and it may very easily break down, because you can imagine the environment is very hostile inside the furnace and air may be flowing at a very large speed because of the flow rate, large flow rate involved. So, it is a very nasty kind of an environment to which these solid products are subjected. There are various kinds of thermal and mechanical stresses which would be acting onto the particle, causing them to degrade as they descend from the top to the bottom. So, therefore, the coke has to have a good strength, and this strength of the coke is also a function of, as I said, that abrasion, wall abrasion, as well as the Barden load and the solution loss reaction or the gasification reaction also. Although carbon is, how does this reaction takes place? This reaction, if you have a carbon lump here and you have carbon dioxide, this reaction takes place at the solid surface. Okay? And at the solid surface, when it takes place, this reaction locally will consume heat. So, as a result of which, what happens is, inside of the coke will be at higher temperature, surface may be at lower temperature because heat has been absorbed, and which will set in thermal stresses, causing small little particles of coke to be thrown away. So, the solution loss reaction is also important parameter in order to determine if the coke does not have adequate amount of strength, then the solution loss reaction will cause the easy fragmentation of the coke near the surface. On the other hand, if the coke has good amount of strength, so the strength comes under physical requirements, and the strength of the coke, there is a parameter called CSR, coke strength upon reduction. Okay? So, that is what we are talking about. So, these are studied in the laboratory. Then there is a reduction degradation index, which is also associated with the reduction, how does the coke degrades as the reduction takes place. So, that we will discuss maybe in the next lecture or so. We will continue, I think, then this. I have taken a little bit longer, so we will continue with our discussion.